Okay, so here we're going to talk about simple harmonic motion in this unit. And to begin, we're going to simply describe simple harmonic motion qualitatively and quantitatively. So think about repeating motions. Motions like a pendulum on a clock, swinging back and forth, or a marble rolling back and forth in the bottom of a bowl. All of these are examples of what's called an oscillatory motion. And all an oscillatory motion is a repetitive motion back and forth across an equilibrium position. All oscillatory motions are periodic, which means that they repeat over a specific period. A period is the amount of time then for one complete cycle of that oscillatory motion. So consider a marble rolling back and forth in the bottom of a curved bowl, right? If you just put the marble in the bowl and allow it to come to rest, it's going to come to rest at an equilibrium position. The equilibrium position is that point where the ball will come to rest when there is no net force acting on it. Now, if you take the ball and you pull it back up, you displace it from that equilibrium and then let it go, there is a net force that pulls it back towards that equilibrium position. However, when the ball is removed from that equilibrium position and then released, the inertia of that moving ball carries it through that equilibrium position and back up the other side. Because of conservation of energy, it's not going to rise any higher than it did when it was released. It's just going to slow down, stop, and then be pulled back toward that equilibrium position again. We call this repeated motion an oscillation, and the oscillation is a result of the interplay between the restoring force and the marble's inertia, something that we're going to see in all of the oscillations that we consider. A key characteristic of an oscillation is the period, which is the time for one complete cycle. So the period would be for the time for the ball to come up and back. An equivalent piece of information is the number of cycles or the number of oscillations completed per second. So the number of cycles per second, we call that the frequency. And the relationship between period and frequency is that they are reciprocals of one another. The frequency is 1 over the period, and the period is 1 over the frequency. Now, because period is the time for one complete cycle, its standard unit is the second. The frequency, the unit for frequency is called a hertz, Hz. Now, you'll often hear about like megahertz or kilohertz or that sort of thing. Just like any other unit, a kilohertz is 10 to the 3 hertz. A megahertz is 10 to the 6 hertz. A gigahertz is 10 to the 9 hertz. So if you have like a radio station that, say, a radio station broadcasts a frequency of 100 megahertz, that frequency in hertz is 1 times 10 to the 8 hertz. And if we wanted to know the period of that, it's 1 over the frequency. 1 times 10 to the 8. The period there ends up to be 10 nanoseconds, or 10 to the negative 8 seconds. Okay, so let's go back and think about this marble oscillating back and forth in this bowl. If we were to graph this motion, we're going to come up with a graph that has the form of a cosine function. So a graph or a function that has the form of a sine or cosine function is called a sinusoidal graph. So a sinusoidal oscillation is called simple harmonic motion. Now look carefully at this graph. This graph here is showing the beginning of the motion at equilibrium. That would be along the x-axis. If we were to actually pull this back, the motion would begin up here at the highest point where we pull it. And then as the ball comes back through equilibrium, then it comes back to the other side, and then it comes back to the equilibrium, goes back to the original point, and then goes oscillating through. So this marble rolling back and forth in the bottom of this bowl is a simple harmonic motion. What we're going to find is that simple harmonic motion is really common, but we're going to see that most cases of simple harmonic motion can be modeled as one of two different situations. The first would be a spring, a mass on a spring, where the mass oscillates back and forth due to the restoring force of that spring. And the second is going to be a pendulum, where the mass oscillates back and forth due to the restoring gravitational force. And what we will find is that for the simple harmonic motion of a mass on a spring, the period will depend on the mass and the stiffness of the spring. And for a pendulum, the period will depend on the length of the pendulum and the free fall acceleration, g. Now, simple harmonic motion can occur when a system has a restoring force that pushes or pulls it back toward equilibrium. For example, for this mass on a spring, this is an air track, so it's a frictionless track that this mass will oscillate back and forth on. When it's at equilibrium, there's no net force acting on it. If we displace it from its equilibrium, this spring will pull it back toward equilibrium. The inertia of the mass will carry it through equilibrium, and then the spring will push it back toward equilibrium again. So the restoring force is what pulls and pushes this mass back and forth. We have to remember, too, that this net force, this restoring force, is given to us when it's a mass on a spring by Hooke's law. Okay? You should remember that this negative sign here in Hooke's law simply tells you that the net force is in the opposite direction as the displacement. So we call this net force a linear restoring force. It's the net force that results in simple harmonic motion. It points in the direction of the equilibrium position, and it's linearly proportional to the distance from equilibrium. In any oscillating system, in any simple harmonic motion, whatever that object is that's oscillating, whether it be a spring, a horizontal spring, or a vertical spring, or a pendulum, the distance that it moves from equilibrium, we call that amplitude. Okay, so amplitude is the distance that object moves from that equilibrium point. And we'll be able to see that oscillation, we'll be able to see that amplitude in that sinusoidal graph. Now, oscillation about an equilibrium position with a linear restoring force, remember, is always simple harmonic motion. If it's a mass on a spring, we can use Hooke's law to tell us the magnitude of that linear restoring force. So now let's take a look at a mass on a spring when the mass is placed vertically. If you place a spring vertically, that spring will just simply hang down without any to some point. If you put a mass on it, that mass will pull that back down to some other point. That will be the equilibrium position for that mass. Okay? Now, if you pull that mass away from that equilibrium position and then allow it to go, it's going to rise up and it's going to oscillate back and forth. We still use Hooke's law to figure out that net force. And your text goes into greater detail on this, and you should take a look at it. But ultimately, what we find is that the role of gravity in a vertically oscillating spring is simply to determine where that equilibrium position is. That gravity does not affect the restoring force for the displacement from equilibrium. You should take a look in your text. It's page 456 for a greater detail of that. So on to pendulums. A pendulum is nothing more than a mass that's hung from a pivot point by a light string or cord or a rod. And the pendulum oscillates back and forth past its equilibrium position. Now, if we do an analysis of the forces on a pendulum, we find that there's only two forces acting on it. You've got tension along the rope, and you've got the weight. Now, as that pendulum oscillates back and forth, there is the component of the weight in that direction of motion. So the x component of that weight will fluctuate. And as it fluctuates, that x component is larger when it's at its furthest amplitude, and then it's at zero. That x component is at zero, its fully y component weight, when it's at its equilibrium position. Then it switches directions over here. So it is that x component of the weight that is the restoring force for the pendulum. So what we find is that the force on a pendulum is a linear restoring force for small angles. We call this the small angle approximation. So we're going to keep our pendulums at a small angle, 15 degrees or less. The result is the pendulum undergoes simple harmonic motion. So now that we've looked at the causes of simple harmonic motion, we can start to develop a mathematical description. Once we do this for one system, and we'll keep your mind on the mass on a spring, once we do this for that system, we can adapt it to any system. The details are going to vary, but the basic form of the motion will be exactly the same. So here we see displacement, velocity, and acceleration graphs for simple harmonic motion of a mass on a spring. When we look at the position graph, we see here is a point where the mass is at its furthest point. If we compare that same time at the velocity graph, we find that the velocity is 0 at that point. That means that instantaneous velocity is 0 where the object is at its highest amplitude. So those are turning points of that motion. It changes direction at each of those points where the velocity is 0. The maximum velocity happens when the object is at its equilibrium point. So if we look at each of these maximum velocities, they correlate directly to the points where the mass is passing through its equilibrium point. Now, if we were to do a series of experiments, and in class we will find that the frequency does not depend on the amplitude of the motion. Small oscillations and large oscillations will have the same period, which is a key feature of simple harmonic motion. We'll explore this a little bit more in detail as we go on. But keep in mind that all these features of the motion of a mass on a spring also apply to other examples of simple harmonic motion. Now, if we compare the acceleration graph to the displacement graph, we see that the acceleration graph is an inverted version of the position time graph. Whenever the position of the object is at its maximum, the acceleration is at a maximum in the opposite direction. And also, if we look at comparison of the acceleration to the velocity graph, we see that when the velocity is at a 0, that is, whenever the velocity is at a 0, that's when the acceleration is at a maximum. When the velocity is at a maximum, that is the point where the acceleration is at 0. And we can look at when the position of that is as well. Now, the position time graph is a cosine curve, so we can write the object's position as this, where the notation, this notation here indicates that the position is a function of the time. And this is a cosine function with the period t. So we can rewrite this in an alternative form. Because the oscillation frequency is the reciprocal of the period, we can write the position of the oscillating body is equal to a cosine 2 pi frequency times that particular time. Now we have to remember that this 2 pi ft is in radians, and that's going to be true throughout simple harmonic motion. So you're going to have to set your calculator into radian mode before working any oscillation problems. Now we can connect simple harmonic motion to uniform circular motion. Both circular motion and simple harmonic motion are motions that repeat. Many of the concepts that we've used for describing simple harmonic motion were introduced in our study for circular motion. We're going to use the close connection between the two then to extend our knowledge of both. Now, suppose a turntable has a small ball glued to it, as we see here. If we were to use light to project this and put a screen in front of that turntable, we'd get a shadow of that ball as it goes around that circle. When we do that, we find that the shadow's motion exactly matches the simple harmonic motion of, say, a mass on a spring. What that tells us then is that uniform circular motion projected onto one dimension is simple harmonic motion. Projecting this ball's shadow onto this screen is equivalent to observing just the x component of the particle's motion. What this means is that the x component of a particle in uniform circular motion is simple harmonic motion, and we can express that position, that x component of its position, using the same equation that we just looked at for simple harmonic motion. A more detailed look at simple harmonic motion too can show us that we can find the not only the position but also the velocity and acceleration for an object in simple harmonic motion if we know the amplitude and the frequency. Then we can completely specify that motion. But what you're going to need to be primarily concerned with is this component, is the position, and being able to connect it to uniform circular motion as well. In the next lesson, we will explore energy in simple harmonic motion, and we'll look a little bit more detailed at pendulums and motion on a spring, and begin to look at something called driven oscillations and resonance. See you in class.